To prepare a buffer, you need to kind of do the opposite of what we were just doing to calculate pH. You have to know what your target pH is and work backwards using the Henderson-Hasselbalch equation. So we know from the last problem on page 8, an NH4, NH3 buffer system has a pKa of 9.26. So I'm just using that same value. Again, the problem would have to give you that information, but since we just did that problem, I'm kind of building on that one. So I'm going to be adding in the information that I have. So I know I have a pH of 9.15 is my target pH range. I'm going to use my 9.26. And notice those two numbers are close. So when you're trying to make a buffer, you need to have something that's close. So I can't use this ammonium buffer to buffer something to a pH of 4.3. It just can't work that way. So you have to choose something that's close to the value of your target buffer. So we're looking for what this ratio is. So we know we need the log of the base over the acid. I'm sorry, it's a really bad G. So we know the NH3 is a 0.10. We don't know what the concentration of the ammonium part has to be. So that's going to be our X value. And I'm going to move left to right instead of down for this, just because I want to save room for a bridge problem underneath here. So if I move the 9.26 over to, and simplify this, I'm going to get a negative 0.11 equals my log of 0.10 over X. Okay. Now, inverse log is something you may not have. If you look on your calculator key, above the log key, you're going to see 10 to the x. So if I take 10 to the x, which in this case is the negative 0.11, that's going to cancel the log function, and then I'll get the 0.10 over x. So when I get 10 to the negative 0.1, that gives me 0.78. Again, I'm kind of moving left to right here, equals 0.1 over x. And I don't know why, but this is the hardest variable to solve for when it's on the bottom. So if you want to make sure you get it correct, some people just have trouble getting this one correct. They do the inverse of that instead of, they solve for 1 over x instead of x. So if you solve for this, you get 0.13 molar. So that has to be your concentration of the NH4, which is the conjugate acid of this. Okay. So now I really have a bridge problem. I know the amount, so there's a lot of numbers in this problem, but just think about basic bridge problems. When we were doing this in Chem 1, we started with what's something we could physically hold. Okay, so the amount of buffer that you have it's going to, or want to make, is going to determine how much mass you're going to need to put in. So again, I'm going to make this nice and long because I'm writing rather large. So I need grams of NH4Cl. Okay. So that's milliliters. So again, if you can do the metric in your head, it's okay if you just make that 0.5 instead of doing that step. But if you're still comfortable with that, that's okay. So I have 0.13 moles of the NH4 per liter. So that's where that concentration comes in that we just calculated for. But I can't measure grams of just an ion, so this is important. AP is really picky about you not just making the assumption. So in every 1 mole of ammonium chloride, I get 1 mole of the NH4. Okay, and the ammonium chloride is really what I'm going to be measuring out, and then I'm just looking for my molar mass of that from the periodic table, which is 53.50. I'm just calculating, so I would need to measure out 3.5 grams of that and dissolve it in 1.1 molar NH3 to make my buffer. Preparing a buffer requires selection of an appropriate conjugate acid-base system. So if we're looking at the phosphate buffer system and we're looking for something with a pH of 7.40, we need to look at all three of the Ka values for phosphoric acid. So it's a triprotic acid, so if we were titrating this, you would have 3 humps or 3 equivalence points. So what I did here was just wrote out the equations for each one. Each Ka value. So phosphoric acid plus water gives you H2PO4 minus, sometimes you'll hear that as dihydrogen phosphate, plus hydronium. Okay, if we go on and take another hydrogen from that, the dihydrogen phosphate is going to become monohydrogen phosphate plus hydronium. And then finally, the monohydrogen phosphate, if we take another hydrogen from that, is going to give you the phosphate ion. So when you're looking at this one, it's the pKa values you want to look at because of that equation. And if we look up here, you will see that we have a pH of 7.4. The appropriate buffer system is the 7.21. So what that means is we need to look at something that it has these two substances. Oops, that's what that was going to do. So I need to analyze the concentrations of these two ions. So, you know, most acids are solutions, but to get these, just like you saw with like the acetates, even it's going to be like sodium acetate, so you're actually finding a salt of these. So we're looking at what ratio of these concentrations do we need in order to create this buffer. So it's substituting in again, so the 7.21 will be your pH, and the 7.4 will be, will be your pKa, and the 7.4 will be your pH. So when you substitute in, you have 7.40 equals 7.21 plus the log of whatever that ratio is. So the ratio is really what we're solving for. So that gives us 0.19 equals the log of x when we move this 7.21 over to the other side. Again, I'm going to do 10 to the minus 10 to the positive 0.19, so 10 to the x, and that's going to give me 1.5. So what this means is we need 1.5 times as many moles of the base as we do the acid. So 1.5 times the HPO4 monobasic to the H2 or the dibasic phosphate. Now, because it's a ratio 1.5 to 1, we'll do it for you. As will 3 to 2. So if you remember, I said more is better. So could we put 3 moles to 2? And if 3 is better, you know, would 9 be better? What limits you is because you're dealing with salts is only so much of that solid is going to dissolve in your 1 liter. So if you would look at 3 moles of the solids, you know, you'd come up with like 430 grams if you calculate that out. So it's really safer to stick with this 1.5 to 1 ratio. So I would have to figure out what 1 mole of that is, and again, it's just stoichiometry looking for grams of that. Okay. So we're going to do a bridge problem. I'm going to have to erase all of this to be able to do the rest. So this is all going to disappear in the next frame. So you can always back up if you need to see it again. So again, we need ions. Anions we're really going to be usually using sodium salts because they're always soluble. So for 1 liter buffer, I would need a concentration of 1.5 moles to 1 liter of that. So that's my concentration. Again, I have to factor in that, what am I getting out of this formula? So for every 1 mole of the disodium hydrogen phosphate or hydrogen monohydrogen phosphate, there's 1 mole of that ion. And then I just need its molar mass. So when you calculate this all out, you're going to see that that gives you a very large mass. So I have 212.94 grams. Remember, our balances only go to 200 grams, so that's something to think about when you're preparing your buffer for lab. So my second bridge setup is going to be the same. They're going to be in the same container, so it's the same 1 liter. So you're putting both of these into the same volumetric flask. So the concentration of 1 mole, again, I'm getting 1 mole of the H2PO4 ion for every 1 mole of the sodium. And then again, it's just a molar mass. And that gives you 119.98 grams. So if you'll notice, the two of these combined were over 320 grams of solid that we're trying to cram into a liter of solution. So sometimes your solubility is going to limit it. So I need a 1.5 to 1 ratio, but there's lots of ways I can get that. I can do a 1 to 0.67 ratio. Okay, that's a 1.5 to 1. Okay, I can do 0.5 to 0.33. So all of those, you can keep going down, and you can, all kinds of different ratios. So you're going to need to know the solubility of your salt once you know what your buffer system is, and you're going to have to kind of play around with it. Again, you're not always going to be in 1 liter either, so we're going to be looking at probably doing some smaller buffers because we don't need those large concentrations. So you'll get the details of what your buffer assignment is in lab.